Okay, so uh, okay, so let us start with photon gas. So we are still doing this Bose-Einstein statistics and Bose-Einstein condensation we have done. And this photon gas, this photon, particles which are assumed to constitute electromagnetic radiation, they are also uh, they also obey Bose-Einstein statistics because they have integral spin. Okay, they have integral spin which is of the order of h over 2 pi. Okay, integral, not non-integral, but integral, not half integral, but integral spin. So what is a photon gas? In order to understand that, we have to understand this figure, black body radiation. So okay. So yeah, so in your fourth semester, fourth semester, when you were learning these elements of modern physics, so I think you must have learned this black body radiation thing, the black body radiation experiment like this. So what happens? There is this arrangement. Okay, there is a small hole here. A light is introduced. Okay, it goes inside this arrangement. Okay, and it gets reflected, and this light gets stuck within this arrangement. Okay, when it enters through the hole, so light is not able to come out actually. Okay, and in such a case, that radiation that we obtain is known as this black body radiation. Okay, the radiation which we get is that of a perfectly black body. Okay, and this light radiation inside this perfectly black body, actually it consists of kind of gas. Okay, one gas, like you have like in your thermal physics class, you have learned about this ideal gas. Okay, ideal gases and real gases. So they have this ideal gas molecules or real gas molecules you have learned. So those molecules actually constitute the ideal gas. But in case of here, in this particular case, so this is also equivalent, okay, to a gas, this light radiation inside this arrangement. And but here, what are the gas particles and what constitutes the gas is the this light radiation or electromagnetic radiation. Okay, so electromagnetic radiations are photons. Okay, photons constitute the electromagnetic radiation, and that forms the kind of gas. Okay, and which is known as photon gas. So there will be this electromagnetic radiation or light. Okay, so it will be trapped inside this structure, and there will be a lot of photons considerably within this arrangement, and this collection of this a lot of photons can be considered to be a gas. Okay, and that is known as the photon gas. Photon gas, or it is a type of boson gas. Okay, so boson gas means it's a gas which consists of a large number of uh, particles which obey Bose-Einstein statistics. Okay, so that is the concept more or less. So let me go back to the PDF, and then we can discuss the PDF. Okay. We can discuss this some note I have written. So to discuss what is a photon gas and some thermodynamic functions related to photon gas. Okay. Okay, so Planck's law of distribution of energy with wavelength in the case of black body radiation can be derived on the basis of Bose-Einstein statistics. Okay, so this thing actually I have written it here, but it is a separate topic, and next time we will read this. We'll learn about this topic. Okay, so how Planck's law can be derived from. It is also in a syllabus, how Planck's law can be derived from Bose-Einstein statistics. Okay. So now, if we have a hollow enclosure, okay, hollow enclosure means the figure that I have just shown you. The walls of which are maintained at a constant temperature capital T. Okay, the walls of the enclosure are maintained at constant temperature T, and a small hole is made in the walls of the enclosure. Okay, so as we have seen, the small hole is also there, so that and the radiation coming out will be those of a perfectly black body emitted at a temperature T. So it is the same figure which I have shown you. So basically, this is the description of that particular figure. So we have an enclosure and we have a small hole through which radiation uh, radiation will come up. Okay, and with that will be equivalent to that of a perfectly black body. Okay, so now the atoms of the walls of the enclosure emit electromagnetic radiations, and at the same time the radiations are observed by the atoms in the walls. Okay, so atoms of the walls of the enclosure emit electromagnetic radiation. Okay, and at the same time these radiations are absorbed by the atoms in the walls. So these electromagnetic radiations, okay, atoms of the walls of they emit electromagnetic radiation, and at the same time these radiations are also absorbed by the same atoms. Okay, so they will emit and they will absorb. Why? Because you have seen in the figure this light which is allowed to move to the enclosure through that small hole, it kind of gets trapped inside the enclosure. Okay, it gets trapped inside the enclosure, and yeah, and so enclosure means it will be incident on the wall, and it will be absorbed by the wall of the enclosure. Again, so I mean, it can hardly get out of the arrangement is made in such a way. So when it is incident, it is absorbed, and when it is emitted, so the light will get reflected and it will keep on moving inside the enclosure. Okay, as shown in the figure. Thus, the atoms in the walls are continuously emitting and absorbing radiation. Okay, so the atoms of the walls, wall means the atoms of this enclosure, they will continuously emit and absorb radiation. Finally, the radiations reach an equilibrium with the atoms of the wall. Okay, so when this thing will continue to happen, this absorption and emission, so they will, so an equilibrium position will be reached, the radiations reach, okay? So the radiation will reach an equilibrium position with the walls of the atom. So what happens at this equilibrium position? At this stage, the amount of energy emitted by the atom per unit time is equal to the amount of energy absorbed by the atoms per unit time. Okay, you see this when what happens in the equilibrium, when the radiations reach the equilibrium with the atoms of the wall. So the amount of energy emitted by the atoms per unit time is equal to the amount of energy absorbed by the atoms per unit time. Okay, amount of units, amount of energy emitted per unit time is equal to amount of energy absorbed per unit time. Okay, this equilibrium radiation in the enclosure is called a black body radiation. Okay, so this equilibrium radiation in the enclosure is known as a black body radiation at temperature T, capital T. So yeah, so when the equilibrium is reached such that amount of energy emitted is equal to the amount of energy absorbed per unit time, and so this this gives rise to a black body radiation at the temperature T. So what is the temperature T? The temperature T was the temperature at which the enclosure was maintained. Okay, this hollow enclosure was maintained. Okay, so have you understood this? So, okay, let me go back to the figure again, so that you can see. Yeah, so this figure, this is the hollow structure enclosure. So light radiation is incident through this small hole. So, and it gets trapped inside this enclosure. Okay. And this once, so the light radiation is absorbed and it is emitted. Absorbed means getting reflected, and emitted means, sorry, absorbed means getting incident, and emitted means getting reflected. So on the walls of this container, okay, so walls of this enclosure, the atoms will, you see, the atoms will, again, this atom here, it absorbs this light radiation and then it emits. Again, at this point of this, point of this enclosure, the atom will get, so the light will get incident and it will be emitted. So this process will continue. Okay, so here, from here again, so this process will continue here within the enclosure. Okay, and with this, and equilibrium will be reached, in which the atoms of the radiations will reach an equilibrium with the atoms of the walls. So at this stage, the amount of energy which is emitted per unit time will be equal to, so in the equilibrium, amount of energy emitted will be per unit time will be equal to the amount of energy absorbed per unit time. Okay. So so this is black body radiation. When this equilibrium position is reached, equilibrium situation is reached, that is called the black body radiation at the temperature capital T. Okay. So yeah, it is something like that. Yeah. And next, yeah. So have you understood this? So this light radiation gets trapped, and so the atoms, so will, each atom will like absorb and emit, absorb and emit, and in this way, some form type of equilibrium, when amount of energy absorbed will be equal to an amount of energy emitted, they will become equal. So we find, we'll get some equilibrium situation, and then and in that case, this equilibrium radiation is known as black body radiation at temperature T. Okay. So this is the thing. Okay, so now let us check this quantum nature of this radiation, black body radiation. Okay, so that is the experimental arrangement. So quantum nature is what is the energy of such radiation. Okay, so that we have to see. Okay, so according to classical theory, the frequency of this radiation lies continuously between 0 to infinity. Okay, so that is what classical physics says. Okay, so this light radiation will have any frequency between 0 and infinity. Sorry, but it has been observed that, but quantum mechanically, it is not like that. It is not that this light radiation will have like frequency in a given range of 0 and infinity. But it has been observed that these radiations carry energy in discrete units or bundles. Okay. So these radiations, this light radiations, black body radiation to be precise, that we have just learned. So this black body radiation has energy, which is in units of bundles, or these bundles are called quanta. Okay, so they carry some fixed values of energy or quantized values of energy. Okay, so why quantized? So the expression is something like this. I hope you have already learned. So their energy value is En equal to N H nu. Sorry. So NH nu. Okay, N is okay. This is N. Okay, not H. Then NH nu. So this is the quantized value of energy of the electromagnetic radiation. So N is an integer like 1, 2, 3, 4. So therefore, these radiations will have fixed or quantized values of energy. Okay. Okay, let me remove it. Okay, so according to quantum theory of radiation of frequency nu, has a quantum of energy h nu. Okay, so any electromagnetic radiation, I hope you have learned about this already. Any electromagnetic radiation which has a frequency nu has an energy equal to h nu. So what is h nu? So h is a Planck's constant and nu is the frequency of the radiation, and it has a momentum value which is given by h nu over c. Okay, like that, where c is the velocity of light. Okay, so now the question is, what are these quanta or bundles known as? Okay, these quanta or the bundles are known as photons. Okay, the quanta or the bundles are known as photons. I hope so. You know already what are photons. Okay, the quantum of energy of the electromagnetic radiations is known as photons. Okay, so the energy is quantized, and this bundle or quantized values of energies of electromagnetic radiation is known as photons. So you see, you must have learned about this thing, no, in your quantum mechanics. This dual nature of radiation and matter. Okay, so dual nature of radiation and matter means radiation means so radiations do have energy, and matter means like some small material particles like electrons, they also show wave behavior. Okay, so waves show properties of material, and material particles show properties of wave. So that is basically the dual nature of matter and radiation. So here in this case, this electromagnetic radiations, here the black body radiation in the experimental arrangement that we have just discussed, so they have energy. Okay, so they have energy, although the energy means they must, and energy means suppose kinetic energy. Okay, so they are waves, electromagnetic waves, but still they possess energy. Okay, so yeah, and this, but see, but if a wave has to possess energy, then we have to always assume that this wave, in this case, in this particular case, the electromagnetic waves are composed of some elementary particles. Okay, and these elementary particles are known as these photons. Okay, so is it clear to you? And their energy value is h nu, and this momentum is h nu over c. Okay, because e equal to h nu, and p is momentum, p is e over c, and p will be equal to h nu over c. Okay, so E equal to this Einstein's mass energy relation, E equal to what? mc square. Okay. Oh, sorry. So E equal to mc square. So P is equal to mc square over c. Mc square over c is mc. So mc is the momentum, okay? Mass into velocity. And but again, P equal to mc. So if you just simplify, E equal to h nu also, E equal to mc square, and also E equal to h nu. So when it is about calculating the momentum, so we can write P equal to h nu over c. Okay. So that is how this momentum expression we get. Okay. Okay, so I'm going to the next part. Okay, so now this quantum of energy of this radiation is known as photons, and these photons can be treated as particles. Okay, since electromagnetic radiations possess energy, okay, in quantized values, and so it may be assumed that they possess some, they have some particles, and these particles are the photons. Okay, those bits may contain some particles, and the particles are the photons. The radiations inside the hollow enclosure consists of, yeah, you see now. So what is a gas? What is the photon gas? That is the definition we have to learn now. The radiations inside the hollow enclosure consist of a very large number of photons of different energies, as they have different frequencies and can be supposed to form a photon gas. Okay, so the radiations inside the hollow enclosure consists of a very large number of photons of different energies, and they have different frequencies. Okay, and that's why they can be supposed to form a photon gas. Since there are a large number of photons, okay, inside the this thing, inside the hollow enclosure, so the combination or the collection of these photons are what right now we have just learned, that these photons are nothing but the electromagnetic radiations. Okay, and or in other words, these photons carry the energy of the electromagnetic radiations. And yeah, and so in case of this black body radiation, since all of this electromagnetic radiation, or better say electromagnetic energy, gets trapped inside the enclosure, so they can be supposed to form something called a photon gas. Okay, because there are a large number of photons inside the enclosure. Okay. Okay, so since the photons have integral spin angular momentum, okay, photons have, it is found that they have integral spin angular momentum, which is in the units of h/2 pi. So these photons are basically bosons, and that's why they obey Bose-Einstein statistics. Okay. So photons have integral spin angular momentum in units of h/2 pi. Yeah. So that's why, and so already we have learned that this is one of the characteristics of bosons, that they have integral spin angular momentum. Okay. And for electrons, which obey Fermi-Dirac statistics, they have half integral spin angular momentum. Okay, half, not full integral, like half integral spin angular momentum. And then yes, so these particles have a half integral spin angular momentum are known as bosons, and they do obey Bose-Einstein statistics. Okay. Okay, so that's basically about this photon gas, the definition of photon gas, and how you can generate a photon gas. So basically, this generation of the photon gas is a simple experiment. You have also learned in your fourth semester this black body radiation. Okay, so that's how this photon gas is generated. Okay, and this photon is actually the boson that obey Bose-Einstein statistics. Okay, so now some thermodynamic functions of this photon. Okay, what is the syllabus? Syllabus, what is it written as? Let me check. Thermodynamic function of photon gas. Okay, thermodynamic function of photon gas. Okay. Okay, so thermodynamic function of photon gas we can calculate as is shown here. So I have taken some values directly. So thermodynamic function means, so we have to, here we have calculated this thing, CV, specific heat. Okay, specific heat at constant volume we have calculated. Then we have calculated this quantity called the entropy, okay, ST, entropy at this temperature T. And then we have calculated this thing, Helmholtz free energy, F equal, okay. And this pressure is also calculated. Pressure is also found, okay. So, okay, let us see how, how we can calculate these various thermodynamic functions of a photon gas, okay. So in order to calculate these various thermodynamic functions of a photon gas, so we have to consider this Stefan Boltzmann law of radiation. Okay, so Stefan Boltzmann law of radiation. So there is this expression I urge you to remember. Okay, so the expression is the energy per unit volume. What is the total energy per unit volume? Okay, so total energy per unit volume from Stefan Boltzmann law of radiation is given by something like this: UT equal to 4 sigma over C T to the power 4. Okay. Okay, so here let me mention one thing. So this is total energy per unit volume, and just total energy without per unit volume, it will be just a multiplication. Total energy will be capital UT. Okay, when total energy, we are talking about energy per unit volume, it is a small u, but when we will talk about the energy, total energy, so it will be same quantity for sigma over C to the power 4, then there would be a multiplication of V volume. Okay. So, okay, anyway, this that will be required later. So I am telling you. Next, okay, next thing is, okay. So UT is the total energy of this radiation per unit volume for sigma over C T to the power 4. So what is the sigma? Sigma is called Stefan Boltzmann constant, and sigma is a value of like this: 2 pi to the power 5 kb to the power 4, and then it's divided by 15 h cube c square. So this is a value of sigma, and which is called this Stefan Boltzmann constant. Okay, so now a heat capacity. Okay, heat capacity of the photon gas at constant volume. So you see, you can measure two things here: either heat capacity or specific heat capacity. So when it is about specific heat, that means it's per unit volume. Okay, so specific heat is about per unit volume, but heat capacity is what you have to do is you have to multiply it with volume. Okay. So, so how can you measure the heat capacity? So Cv equal to du over dt at constant V. So, okay, du over dt at constant V. Okay, so this is the formula. So this U is just now I have shown you here. Okay, so capital U T equal to, so this expression, this particular expression multiplied by V. Okay, now if you just differentiate this expression with respect to T, then what we get, 4 multiplied by 16 sigma T cube by C. Okay, so this is the expression which we will get. Okay, so this will give you the heat capacity, and if you want to measure the specific heat capacity, so that is just like Cv. Okay, Cv is equal to specific heat capacity, capital Cv over capital V. Okay, in that case, the V quantity would not be there, but specific, but heat capacity V quantity would be there. Okay. Okay, so that is how you can calculate the heat capacity of this photon gas, okay, or radiation. So law of radiation means this is the specific heat of radiation. So now how we can calculate this thing, entropy. Okay, entropy can be calculated by a formula like this. Okay, so we can integrate it. Okay, you can integrate this expression to find entropy. Okay. So in order to calculate entropy, this is the formula to calculate entropy. So entropy is basically, so it is dq. So yeah, it is something like this. So CVT over T, and you have to integrate it with respect to temperature. Okay, entropy. Just give me a moment. I'm checking something. Yeah, so okay, so entropy formula is like this, something like this. Okay, so change in entropy ds is equal to dq over t. Okay, so this is what we learned in thermal physics, if you can recall it. So dq is the heat supplied, or here it is du instead of dq, heat supplied or heat supplied or energy. Okay, same thing. So cv dt, cv dt. Yeah, so in place of dq, okay. So in place of dq, we can write it as cv dt. Okay, cv dt over t, because cv is equal to dq over dt, dq over dt. Okay, so here it is u, of course, but this is what we learned. Okay, of course it is the change in the letter, but it's the same thing. So we learned it as dq, but here it is du. So ds equal to dq over t. Okay, that is what we learned. So dq can be written as cv dt. dq is written as cv dt. Okay, so like this, ds equal to like this. So now just integrate this, you can calculate the entropy, and here this quantity will be cv over t dt. Okay. Okay, so that's how we get this formula. And now just replace the value of cv, which you got here, this one, 16 sigma over c t cube v, 16 sigma over c t cube v. So here is one t in the denominator. So t cube gets cancelled by t. We'll be left with t square dt. So just integrate it from 0 to t, from temperature 0 to capital T, and you can calculate the expression for entropy. Okay, so I hope you understood how entropy is calculated. Just remember this formula. Substitute the value of cv, and we can calculate entropy. So that is another thermodynamic function. So we have calculated the specific heat. We have calculated heat capacity, or you can also calculate the specific heat, then entropy. Okay, so now we can derive, okay, so now this Helmholtz free energy. Okay, Helmholtz free energy is also another thermodynamic function. So Helmholtz free energy is, if you remember, F equal to U minus Ts. Okay, this was the formula. So U stands for the internal energy, and Ts stands for temperature multiplied by entropy. So U is this energy. We got it somewhere. U is this thing, 4 sigma T4 over C. 4 sigma T4 over C. Oh, okay, U is, so here we are multiplying with V, because here it is capital U. Okay? So when it is capital U, you have to multiply. So, okay, so what is the relation? Capital U is equal to small u multiplied by V. So small u is the energy per unit volume. Okay, and capital U is the just the energy. It is not per unit volume. So small u is, so that is why when we are writing it as capital U, we are multiplying it with this V, volume quantity. Okay, but earlier case it was just energy per unit volume, minus Ts. Okay, minus Ts. Let me go back. So minus Ts. So T we have here, T and S. S we have here. Okay, as we just found out. So T means temperature multiplied by this. So we get this quantity. So F equal to, we get this. Okay, F equal to, we get this. Yeah. So this is just simplification. If you just simplify this, so you will get this quantity. So this gives you the Helmholtz free energy. Okay. Yeah. Okay, so then the pressure, okay, this, so how you can calculate the pressure. Pressure is calculated by this relation minus dF dV, okay, at a constant temperature. So dF dV at constant temperature. Yeah, okay. So this expression. So pressure. So how this has come, I'm not sure. This formula, but dF dV at constant temperature, you will get something like this, a quantity like this, and this quantity is 1/3 of U. 1/3 of U means energy per unit volume. This, yeah, okay. U equal to okay, small u of course here. U equal to 4 sigma over C T4. U equal to 4 sigma over C T4. But there is 1/3 here, so it will be 1/3 U. U equal to 4 sigma T4 over C. Okay, so pressure equal to 1/3 U. But U is again, we know U, small u is again capital U plus V, so PV. Okay, so small u is again, we have just discussed capital U plus V, capital U plus V. So we get PV equal to U/T. Okay, so that is the thing. Okay, so is it clear? So this, okay, P equal to F. So this is what I'm wondering. So this, what is the formula?
I think this comes from this canonical ensemble formula.
This one. Okay, canonical ensemble. Okay, so for classical, this thing. Okay, F equal to U
Yes,
minus
sir.
F equal to U minus TS. V, P. Okay, so anyway, so yeah, you can just remember this. It is the rest of the things is easy. So this is kind of the like this equation of a state, kind of PV equal to energy over 3. Okay. Yeah, so that's all about this thing, this photon gas, and what is a photon gas, and various thermodynamic functions. But I think I can also include one topic here, which is the difference between photon gas and this real gas, ideal gas. Difference between photon gas and ideal gas. One small topic I can also include, but I think I will just add it, add some document from internet to your Google Classroom, and you can also read it from there. Okay. Okay. Anyway, so I think that's all about photon gas. So next class we will learn about this Planck's law from Bose-Einstein law. Okay. Anyway, so please take the screenshot, and also you have the test from 2 p.m. Remember, okay? From 2 p.m. you have
Yes,
that.
sir.
Yeah, remember that. So you can take break after the first test, and then you can start it. Okay, so all the best for your exams.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.